Hey guys, welcome back to the channel. Today we're gonna be exploring linear versus binary search. Okay, let's first start with linear. Okay, let's start with linear. Okay, because it's the easy case. Okay, suppose we're given an array. Okay, and the keyword here is sorted. Okay, it has to be sorted or binary search would not work. Linear search will work regardless of sorted versus non-sorted, but binary search wouldn't. But so let's just treat the cases the same. Say we're given a array called sequence. Okay, and let's use a 0 1 2 3 4 5 6 7 8 9. Okay, again, I specifically chose this test case because our indices happen to be exactly the numbers. Okay, the indices happen to be exactly the number. Okay, so we were given this and asked to find some kind of target value. Let's explore 3 different target values. Okay, in the first case, our target value t1 is equal to, let's say he's at the beginning of the array, he's about 0. Okay, so with linear search, what we do is we start at the first element in the array, and then we ask ourselves, is this our target? If it's yes, we return that value, or the index in this case, depending on what you're asked to return. If not, we move to the next value. Is this our target? Is this our target? If this isn't, is this our target? If this isn't, is this our target? We keep them. So in the first case, okay, t equals 0. This would only run once, because once it starts with the first one is the target, it will run once. So in terms of time complexity, his big O of n, where n is the length of the array, in this case n is 9, divided by n minus 1. Okay, which essentially this is the same as saying this is equivalent to big O of n over n, which is equal to big O of 1. Okay, essentially, right? That's if our target is the first element. Now let's take a situation where our target is somewhere in the middle, say 5. Our target is 5, so say t2 equals 5. Okay, now in this case, he's gonna go through the first guy. Is this our target? No. Second guy, is this our target? No. Third guy, is this our target? No. It's gonna keep doing that till it finds the target at 5. Okay, which, let's assume it's in the middle. Okay, so in this case, our big O is gonna be big O of n divided by n minus n over 2. Okay, because he went halfway. Okay, so which in this case, it just simplifies to big O of n over 2, because it's only gonna go half, so which is just big O of n. Okay, if he goes halfway. Okay, so let's just big O of n. Okay, now let's say he's in the end, t3 is the last element, 9. Again, we usually don't know what element we're looking for, we don't know where he is, we just have to go through it and check. Okay, this is obviously, it's gonna start with the first one. Is he here? No. Go to the next one. Is he here? No. All the way till he gets to the last guy, 9. Okay, this is obviously big O of n because he literally had to go through the array. Okay, so we can just call this worst case scenario, because that's what big O complexity is. It measures worst case scenario. Worst case scenario with a linear search at time complexity is gonna be big O of n. Worst case scenario. Okay, where n is the length of our array. Now let's see binary. Okay, in binary we're gonna have the same 2 test cases we had for linear. Okay, we're given the exact same sequence. Okay, this case equals to the exact same 0 1 2 3 4 5 6 7 8 9. Okay, again, chose this on purpose because the sequence happened to collide with our indices. Okay, so now we're given our first guy. Okay, so binary sequence, this is typically how it works. It has 2 pointers, a left, a right, and a middle pointer. Mid is usually right, midway between left and right. Okay, it's gonna ask ourselves, is the element we're looking for, again, binary only works if it's sorted, but it's gonna ask, is our target element, whatever he is he bigger than this middle element? If he's bigger, we can just let go of this guy and only search. So essentially we move our left pointer. So let me just undo this. essentially, if it's bigger, we'll move our left pointer right here, okay, and therefore our mid pointer will be somewhere in between. So essentially what we did was cancel the rest of this array, obviously if it's bigger, okay. If it's not bigger, okay, let's go back to what it was originally. Okay, if he's not bigger, okay, meaning he's smaller, right? If he's smaller, we're just gonna essentially cancel this guy. How? By moving our right pointer here. So essentially our mid pointer goes somewhere here. So all we're left with is this smaller array. However, third case is if he's exactly equal. If he's exactly equal to the mid, then boom, we get what we want at the first try. We just return the mid. Okay, so let's again explore it using the same test cases we used for this. Okay, so let's say T1, so our target is 0. So obviously we know what L is. We can just write an if statement, say if is L, return L. So literally this is gonna run in O, say or 1 typically. Okay, say is the last element, but keep in mind that, okay, each loop of this, okay, like we showed, okay, let me take this away. Each loop of this, essentially if it's bigger, so say our target is less than, okay, let's go back. T1 equals 0. Okay, in this case he's less than our mid. Okay, so we're literally eliminating half. Okay, so each loop we do till we get the answer, we're always eliminating half, meaning our big O is always gonna be, keep in mind we're always eliminating half each loop. Okay, so our big O is always gonna be n divided by 2 raised to power x. Okay, what is x? X is the number of times you're gonna have to run. Okay, in the case, let's say n equals 8, meaning we're given an array of 0 to 8, okay, roughly to 8. In this case n equals 9, but let's say n equals 8. In this case our big O is going to be, how many times do I need to run? Okay, so pretty much essentially you're asking the question, okay, you're asking yourself how many times do I need to run to get to get up to 8? So essentially this x is going to be 3, because 8 equals to 2 to the power of 3. Does that kind of make sense? I know it's kind of tricky, but just essentially what should you do, what you should do to solve this equation. Again, this is not a mathematical proof of how it works, but 2 to the x equals 8, where 8 is the length of the array you're given. So x is essentially equals to log base 2, right, of 8, right? So pretty much where n is the length, time complexity with a binary search is always big O of log of n, always. Okay, for binary search, which is a lot faster than linear. So let's put all this knowledge into code and see how it actually works. So now I'm gonna quickly code up a linear search. Okay, so let's say def. Okay, he takes in a sequence and a target. Target is what we want to find. For now, let's say pass. For now, okay. Now let's define our driver code that's gonna call this function. Let's define our driver. Okay, just so we can play around with it and have different values. Let's just say, let's create let's kind of have some fun with this. So let's say our sequence. Okay, I'm just gonna use sequence is just equal to a list of range. Okay, I just want to create a list from 0. Again, it can be forever to, let me create a variable called upper. Okay, and I'll show you what it does in a second. Okay, so let's say upper equals 20. Okay, let's go ahead and print this list just to show you what it does. Okay, so it just prints. Again, once you use the range operator, it's always exclusive of the upper bound, so it prints from 0 to this. You know what, let's also create a variable called lower. just to give us our lower bound. Okay, negative 20. Okay, so now let's see. Okay, this is our list. Okay, 2020. Let's have some fun with it. So let's increment him by 2, so only even numbers. So he increments by 2 every time, only even numbers. Okay, so now let's also decide what number we want to find, okay, which is our target. So let's say target, and just so target is different every time, let's just create a random number. So let's just say from random, and I'm just importing a random module. I'm importing the random module from Python. Well, not the whole module. Okay, just a specific package in that module. Okay, so now I want to say, give me a random integer, okay, between our lower and our upper bound. Okay, which is what I'm saying. And I'm also gonna go ahead and print this random integer so you guys can see what it is. So our target is target. Okay, let's go ahead and see. Okay, so our target is -2. Our sequence is this. Okay, so we have this, guys. Okay, so now I'm gonna go ahead and call this function now. Just although right now he's not doing anything. Okay, so our function call is right here. So I'll just Ctrl-Z and print. Okay, right now he's not doing anything, but he should print whatever the value is once I call him. Okay, so now let's actually put the meat and potatoes in this code. Okay, so let's say for I and num, okay, in enumerate. Okay, so I'm just literally going through the sequence. Okay, if the specific number we're on equal our target, the number we're looking for, okay, we want to return the index of that number, which is I. However, if we go through this for loop and we never find him, we want to return none. None is a type in Python, just meaning he doesn't exist. Okay, let's go ahead and try this. Okay, give us an error. Oh, indentation. Oh, okay. Yeah, we have to indent this. Okay, because they use statement. Okay, boom. So our target is 19. Obviously, this is only even numbers in this array. 19 doesn't exist, so that's why we get it now. Okay, let's try something else. Now our target is 20. 20 also doesn't exist because he stops at 18. Okay. Okay, now our target is -16. He does exist, and he's the second index, right? 0, 1, 2. So this works. Okay, this works. But now let's try the same implementation of the same thing using a binary search. Okay. So def. Okay, I'm gonna call it binary. Okay, we're implementing the exact same function but using a binary search. Okay, we just want to see what it is. So with binary is pretty straightforward. First we define a left and a right pointer. Okay, our left is always equal to 0, the start of array. Our right is always equal to the length of our sequence -1, because arrays are 0 based. Okay, I don't want to put a space here. Okay, we have our left and right, so we just want to say while our left pointer never meets or passes our right pointer. Okay, because we never want the left to go. Okay, kind of like we explained on here, we never want the left pointer to go beyond the right pointer, right? Okay, while this never happens, okay, calculate our mid. Our mid is always equal to our right plus our left divided by 2, floor divided by 2 to avoid decimals. Okay, so simple. Say if the sequence at our midpoint, if the midpoint equal our target. Okay, if it's equal to our target, what do we want to do? Obviously, we want to return his index. The index is mid. Okay, elif. Okay, elif what? Elif target. Okay, our target is less than this sequence. Okay, he's less than it, meaning he exists somewhere on the left hand side of this sorted array. So what we want to move the right. Okay, we don't care, we want to move the right. So right is gonna be equal to mid -1, kind of like we explained. We'll move the right inwards. Okay, Now else, there'll be an else case. Else meaning our target is larger than our midpoint, the value at our midpoint. So we want to move our left. So left is just going to be equal to mid plus 1. Okay. Then if we done this all the way to where L and R are equal, or L becomes past R, the while loop will stop, and then we return none, meaning he doesn't exist. So let's go ahead and call him again 2 with a print statement. I will test him for a few target cases just to make sure he kind of works. Okay, let's make sure we call him binary search. Okay, now let's run. Okay, 6 seems correct. Let's run it a second time. None. Okay, that's for both binary and linear. Okay, none again because we're negative 15. None, only even numbers in here. 15, none. 15. Oh, is 15 in there? Okay, yeah. Target is 10. Okay, yeah, 10 is 15. So I think it works. Okay, so now let's go ahead and time these functions just to see who does faster. So why I like Google Colab Notebook is it provides us with something called time it %. Time it, which kind of gives us how long a function takes to execute, or just any operation takes to execute in general. Okay, now let's run it. Let's see. Okay, boom, it's done. Okay, so the binary version took 781 nanoseconds, so which is 0.8 microseconds, while this took 1.3 microseconds. It's not too big of a gap. 1.3 microseconds versus 0.8 microseconds, not too big of a gap. But however, let's see what happens if we keep expanding the range of our upper lower bound. So I'm just gonna say from negative 200 to 200. So I expanded it by a lot now. Okay, and I'm gonna go ahead and stop. I'm not gonna print them because that's gonna be a lot of printing. So I'm just gonna go ahead and remove these print statements. Okay, now let's just watch. Oh, I'm sorry. Okay, let's remove the print statements. So let's just watch what the timing function does. Okay, now that we pretty much 10x our range, the first function, okay, executed in 9 microseconds. Okay, while this executed in 1 microsecond, right, roughly 1.5. So literally about 7 times faster for the second guy. Okay, the previous time it wasn't up to 7, they were almost close. It was 0.7 versus 1.3. It wasn't up to double the speed, but now it's almost 7 times the speed. So let's go ahead and increase it one more time. Just put 0 and 0 and see how long they take. Okay, as you can see, this took, oh wow, more than 50 times, about 50 times this. So as the input continues, as the search area continues to scale, this guy doesn't do bad. He doesn't do too bad, right? He went from 0.8 to 2 between the lowest case and now, while this guy has gone from 1 microsecond, 1.3 to 100 microseconds. So this is why binary search is always better than linear search when the input array is sorted. That's it for the video. I hope it was helpful. I'll see you next one.